Hey, John here. Let's talk about classes in C++. Before we get to where we're going, let's talk about where we came from. A class in C++ is patterned after the idea of a struct in C. Now, C++ supports both struct and a class, and there's almost no difference between the two whatsoever in C++. C, on the other hand, has no classes at all, and a struct in C has far more limited functionality than you can use in C++. So let's start with the beginning here with a struct, because you actually do see people use these in C++ programs. I'll try to circle back at the end when it makes sense to discuss the differences and why you would use either one. Okay, so to start with, let's create a struct. It's short for record structure, okay? This is the name of this record structure. By creating, or more accurately, I should say, by defining one of these things, what I'm doing is I'm introducing a new kind of data type into my program. I'm creating a struct called foo, or I could say class foo if I wanted to. Now, what this represents, like I said, is a record, an idea of a list of variables in one bundle. Okay, so this is a container of some kind. If I create a foo, like I do down here, just like I could create an int or a double or a float or an array or something like that, I can create a foo now. And when I create one, what I'm getting are two integers. And this is the notation that we use to refer to those values of these two fields in this record structure called a foo. So if I say foo x, I end up with an a and a b. Well, I can't just say x equals something, right? What do? I want x dot a equals 1. That assigns a 1 here. X dot b equals a 2 down there. I can then print it out like this. So let's go ahead and compile this. All right, run it, and we can see A is 1 and B is 2, right? Now I can also do this because it's, once I've created a new kind of data, I can do anything I want to it using any of the operations I'm already familiar with. So I can create a foo pointer to foo like this. And if I want to, I can say p foo equals the address of x. Now p foo points at x. All right. We can go ahead and leave this in here. And then we can also create more stuff. I can say p foo. And now I use this right arrow. Okay. By putting a right arrow in there, what I'm really doing is saying take the value of this pointer, and the arrow to me, that looks like a pointer, and then go get the A field from the thing it points at. I can say equals 23, and then I can put p foo right arrow B equals 99. Let's make that look nice and purty. All right, and again, I can print these things out. I can say A equals, and then again down here, say p foo right arrow A, and I can say p foo right arrow B. And again, it runs as we would expect. We see both versions coming out like this. So there's two different ways of dealing with these things. And if I want to, I can create a reference. Okay, and I have to give it a value because it has to have a value when I define it. I can give it a reference to x here. All right, now what happens? Well, ref is an alias of x, so if I want to, I can just simply do this, and I can use my ref instead of x in this notation here, because ref is an alias of an instance of foo. All right, let's go ahead and compile this, and it does what you would expect it to, because I modified it through that pointer. Pfoo, right? Now, let's do this just for fun. What happens if I do this? now I've created a reference to a pointer to a foo. All right, again, just for total completeness here, let's go with, what will this one be? Ref P. It's a reference to a pointer, so I have to treat it now as a pointer, like that, okay? And obviously that works. Now I just kind of threw this in just to be super complete, rather, this one down here. Because again, if I can create a thing, I can have a reference to it. I can create a pointer to it. And because a pointer is just another thing, I can create a reference to a pointer just as easily. All right. Now let's get rid of all this excessive, unnecessary detail, because it's not necessary to understand classes. That's just how you interact with them. If you have the class instance, or a reference to an instance, or a pointer to it, or a pointer to a reference, or whatever else. Okay, so what's the takeaway here? I create a foo. What I get are all the variables inside the foo in one big bundle. All right? Now, let's look at the difference between a struct and a class. What's going to happen in here? I get all these errors. Foo A is private within this context. This is private. It's private, private, private. Can't do this. So this is the first thing. And this is the only thing that I'm aware of that's different between a class and a struct. When you go from C to C++, the idea of a struct changes. One of the things that happens is C++ adds what we call methods, or member functions. In addition to putting variables in a bundle, I can actually put functions in here. I can create new functions in there, okay? The other thing that happens is you have a notion of privacy. Privacy, the concept of privacy, is not present in C. Therefore, it's not part of a C structure, all right? And when we add the concept of privacy, in order to be backwards compatible with a C program, by default, a struct has no privacy whatsoever, which means if main creates an X, it can reach inside of that X using this notation, and it can dabble with these variables in here. If I make this a class, or if I explicitly declare these as private, I end up in a situation where main can no longer reach inside and dabble with those variables inside that structure, okay? Now, that gets us to why have both kinds? Well, for traditional reasons, if you do need an object in a C++ program where all of the members are what we call plain old data, which means that it is what I call a native data type, right? An int, a float, a double, and things like that, or an array, right? You could put an int, X in here, like that. You could even put another struct inside here, as long as the struct inside here, like if I come up here and I type struct X, like that, I can put an X in here. Now I got to be careful because this X and this X is the same. It's a bad name. Let's call this XXX so that it's really unique. All right. Blah, or something like this. Now what happens is this is still all plain old data, even though it comes from another struct, because this is plain old data inside of here, right? I can also say, R and whatever, just to make this more interesting, okay? This is still all just plain old data. Foo itself contains, directly or indirectly, as the case is down here, plain old data, what we call a pod data type, okay? If you're going to create something, an object, and it's going to be a pod, and all the data is public, people to this day, when they're writing C++ apps, still use struct. The fact that it is a struct suggests something to the programmer in that context, that everything in there is going to be pod and it is all going to be public. All right. Other than that, I never see them. All right. Doesn't mean they don't exist, but that's the kind of thing you see. So if I do this as a class, the default access is private, but I can go like this and make it public. All right. Class with public right here is the same thing as a struct. If I declare something as a struct, I'm suggesting that my intent is that the contents of that struct is pod, okay? If we do this, by the way, let's just show how we access those other things in there. If I wanted to get to this Q and the R in this situation here, what would I do? I would say a dot blah dot q equals 123. And that makes sense. If x dot a is the name of this variable in here, well, then x dot blah must be whatever this is. And since that's a structure, I just put another dot over there and I put the field down there and I just keep on going. This can go on forever. 80 levels deep, a dot b dot c dot d dot e dot f, whatever it takes, you can do that sort of thing, all right? So to show you that I'm not lying, let's go ahead and print this out. What am I going to do here? I'm going to say whatever. xq, x block q equals this thingy. Blah, blah, blah. And we go in here. I'm going to get this comma out of here. Hard to type and talk at the same time. It really did. All right, no compiler errors, it works all fine, and that's what you end up with, that sort of thing, okay? Now, we don't need to talk about, these recursively included and defined things. I just wanted you to understand what the notation means and how you reach in and grab stuff. All right. Now, in C++, you don't do this. You make your stuff private. I make them explicitly private. Even by definition, we know that the default is private because it's a class, because that's the rule. I make it explicit anyway. All right. So what else can we do with these struct and class constructs in C++? We have these things called member functions, right? Let's make these public. All right. And this is kind of what you sort of see. You might see some public things and some private things in an object like this. So let's put a method in here. Let's say void func. Let's say it doesn't take any parameters, right? Let's actually define it in line. We can put the whole source code right inside here, okay? This is one way to do these things. Now let's look and see and do this, right? Now, what happens in this func is that I have this new notion, this context when this thing runs, x.func, right? You refer to things inside of this object by name because I have a value of a thing of type foo. I can reach inside it with a dot. If I had a pointer to a foo, I'd use the arrow. Same thing as you saw before, okay? This will execute this func method. Now, I cannot do this anymore. Let's go ahead and compile it. You'll see it's going to gripe about private, okay? So let's go ahead and comment this out and make it all public. And you can have more than one public in here. It's okay. Sometimes you see private stuff followed by public stuff, followed by more private, more public. It has to do with how you arrange your code. For now, let's do this, okay? It all ran. And look what happened down here, A1, B2. Let's make sure we all understand what just happened here. I reached inside my foo object and initialized some values I call x.func. Func comes along here and he prints out this A and B. What A? What B? Where did these things come from? All right, so this has a context. This function, this method of class foo, when it runs, the variables in the scope of this block include, just like any other function, anything that's defined or declared inside here. It includes any global items that I might put up here. Okay? And it also includes these variables here because these are also members of the same class that func is a member. Okay? Now, let's make sure that we're real clear on what that means. Because what if I have more than one foo? What if I have a foo y down here? And I say y dot a equals 10. And then I say y dot b equals 20. And then I say y dot func down here. I have two separate foo objects now. I have the x foo and I have the y foo. When yfunc runs, the things that are in the scope of this executing method are the variables and their values of the foo on behalf which this func was executed. So this will give func here access to the A and B values that are associated with the instance of foo called y. So when I run it down there, I'm going to see the 10 and 20. When I run it up here, I'm going to see the 1 and 2. All right? And to really drive the point home, let's call xfunc again after we've called yfunc. These are separate things in every way, shape, or form. Okay? You'll see I get 1 and 2, I get the 10 and 20, and now I see the 1 and 2 again. So these things are completely independent of each other. I have two instances, right? This is what we refer to this thing, instance of foo called x, all right? And this one is an instance of foo called y, all right? So this is the most basic terms, is one of the things we do with these things, all right? Now, you know, is this really what, you know, why is this so great? Well, if you use them literally the way I drew them here, you know, this is useful. It can keep all your code that's affiliated with these bundles of variables in all one spot, all right? But if anybody can come along and start poking at these things any old time, how do you know that these things have maintained their integrity? So this thing goes way beyond this. That's what this privacy is all about. If we do this, now the only code anywhere in your entire system that's allowed to read or write or access in any way these variables A and B are the member functions of this class. Now we've got a whole new concept of power when it comes to debugging and maintaining the quality of your software. If you create a class called foo and you need these variables in here, and you write a bunch of member functions and you fully debug them, and everything works perfectly, you give this class to someone else and they use it in their program. Let's say a problem comes up. Well, as long as you know that you've debugged all your methods okay, you know that the person that used your class is not allowed to go in here and diddle with these things. Therefore, you can be assured that your code was safe. Okay? Now, that's not to say that somebody down here didn't corrupt their own memory and destroy it by accident. That's a whole nother thing, right? On the other hand, as long as your code behaves, the integrity of these values over the course of time will always be known to match whatever functions and availability you give to the rest of the program world through these functions. So let's say we create a function like this called like init. And maybe this can go like this, and we can say A equals 0, and we can say B equals 0. We know this is illegal now, down there, because they are private, right? So the only way to set anything right now would be to call this init function, right? X.init, it'll set them to 0. This down here is also illegal. We can call y.init. I'm going to comment out this y.init. We don't need to call that again anymore. Why did I comment this out? I wanted to leave it filled with garbage. All right, so this one will print garbage because that's what happens when you allocate something on your call stack, an automatic variable, and don't give it any initial value at all. Right? Up here, he's going to initialize it, and then he's going to call that func. Now, I don't know, there might be zeros in there, and in this case, there are not when we have the y instance of this class, all right? So if y were to then initialize itself like this, it too now will be set up with zeros, okay? Now, we know that the only thing that can ever happen in this object is init. Init is the only thing that can ever change the contents of A and B. Unless some, illegal, corrupt thing has happened to the running program. Like memory corruption is always a problem, and you can't avoid that with C++. But as long as memory is not corrupted, you can know that this is well behaved, right? Sometimes you see routines like this in here. In fact, if they're super short, I'll do this and just put the code right over here. I'll say A equals I, like that. Maybe you'll have a set B over here. And you would say B equals I. Okay? Now he could say, maybe he would say instead of init at this point, he could say set A, 1, 2, 3. Then he would say set B, 4, 5, 6. Oops. That's because, well, this is what happens if you don't put the y dot in front of it, right? It says it was not defined in this scope. And that makes perfect sense because I don't have a set B. I have to call set B on behalf of something whose type is class foo up there, all right? Typo on my behalf. So there you go, and it makes sense. I called set A and I called set B, and set A reached in there and set these variables for me. All right. Now you could argue, well, what's the point of all this? All right, a million lines of code. Why don't I just reach in there and set these things? Well, this is a very trivial example of a very trivial thing. You're never going to get paid to write trivial programs. The complexity will escalate exponentially over time when we create real programs, okay? So these set, and you'll see sometimes there's get routines. It's get A and get B, and they'll simply just return the current value of A and B, at which point you've fully exposed this object. However, while you've given all other code full access to the contents of your foo class, you've still provided this gauntlet, so to speak. They can only do it by going through these functions. If you ever find out that you have bad data in one of your objects, rest assured the only way the data could have gone awry is by someone calling these functions. In other words, I don't have to go through the entire program looking for all possible references to someone setting these A and B variables to some crazy value in order to figure out what wrong, because I know it happened right here. Especially if I name something A and B. Do a global text search sometime on your program for all instances of B. It's a disaster area. You can look for set underscore A, set underscore B. You have a few less hits, easier to find. You know what else you can do? You can run this program inside GDB, like I've shown you before, and put a breakpoint on there and see what's calling this function. There's some other utilities as well. If you use Doxygen to comment your code and you run it through the Doxygen tool, you can generate a graph that shows every place in the code that ever refers to and calls set B, and what calls set A, what calls init, what calls function, so you can actually get a mapping of your entire application. I'll record a piece on that at some point as well, and you can see how that works. But again, this only is true provided that you put this little gauntlet in place and that you use the right documentation tools, okay? I would argue you'd be hard-pressed to not be able to debug a problem if you know everything that refers to everything else in your program and when it's called. You can find everything. That's the biggest problem with C++ apps, in my opinion, with all this these classes, and we'll see inheritance and all this other stuff. It's kind of hard to figure out what's going on. So you need to figure out how things are related, okay? And by putting this gauntlet in place, you know the only thing that can touch anything in here are these member functions. And now it becomes valuable. You can also do this. Here's my poor man's version of this, right? If I want to, I can say cout. Let's expand this out a little bit. We'll put some more code in here. You can print stuff inside here. You know, someone set A to I, right? And I actually do this sort of thing in my programs from time to time. If I want to have runtime debugging built into my program, look what happens here. Oh, somebody said A to 123. Okay. You can't do this if you let somebody just say A equals, 12 or something like that. All right, it gets way out of hand. No, I can actually put little traces. I can leave, footprints in the snow, as it were, as we say. All right. So we have these things are called access. Actually, this is called a mutator. Mutator. If you wrote a get routine, you'd look at like this: get A, and you'd say return A. This is what we call an accessor. We might as well finish our program and put a get B in here, all right? And return a B. Now we have everything. We can set anything we want. We can get anything we want. We've got accessors. We've got mutators. And we've got other utility functions that do things with the data in this object as well. You can start to see this is what goes on here. Your program code starts disappearing from your functions over here in main and starts migrating into these methods over here. And it keeps everything all bundled together. If again, all the things related to a foo is in one nice package, okay? Not strewn all over the place. And some people have trouble naming their things in meaningful ways. And even if this was poorly named, like foo, funk, and init, I still know that whatever a foo is has all of its pieces in one bundle. And there are no more because these are private. And then the only thing that interacts with them are these methods down here. Now let's go to the next step. Because an init function would be really useful, and because you're going to probably call it almost all the time anyway, let's get rid of this. What happens is, what if someone forgets to initialize it? Or they forget to call the set A and set B down here. Then you have this problem where your A and B variables are garbage. And again, like I said before, the idea of a class is I'm the only one, these member functions down here are the only things that are allowed to touch this. If I allow someone to create a foo and forget to do this, I have a problem. Because my own methods could ultimately fail, in theory, if there's a bad value on one. Let's say B becomes set to a 0 by mistake, and I have a division in here by B somewhere. I end up with a divide by 0 error, right? Well, I should protect against that in here, okay? So I took the liberty of calling that thing init. In reality, what we can do is we can declare a function called foo. This has no return type. Notice there's no return value over here, okay? If I name a function the same as the class, what happens is this will be called when foo is constructed. This is a constructor function. Why? Because it has the same name as the class. What this does is down here, when I create X, that constructor will get called. And when I create Y, that constructor gets called again on behalf of the X and the Y. And when I come into this constructor, this is what will happen. Let's put a cout in here like this and say constructing let's also introduce another idea called this. As we will see in a moment, the word this, and even my editor knows there's something special about it. Look at how it's yellow, right? All these special words have a different color. Using, private, public, this. This is a word. It's a key word in the language, a reserved word in C++ that represents a value that is the address of the object, the instance of this object that is executing this method. So by doing this, what happens is I'm going to print constructing colon, and then this is a pointer. This is a pointer to a foo. What happens when we print out a pointer? We get the hex address number out of it. Okay? So when this thing runs, it'll say I'm constructing, and it'll print the address of the instance of foo that's being constructed. Then it'll set these values to 0 down here. And we'll see it get called once for X and once for Y, and they'll have two separate addresses, and they'll probably be 7FFFF something, because that's where the program call stack is, and there we see I'm constructing a foo at this address here at CE588. Later on, it says I'm constructing another one at CE590, which is just a few bytes beyond that, right? What's 88 in hex plus 8? It's 90 in hex. These are two integers. Each one of them is 4 bytes. So it makes sense that a foo, if I take size of foo, it will be 8, because there's 8 bytes worth of variables in here. Okay? Now, setting everything to 0 every single time, especially if you're going to immediately change it to something else, might be inefficient. So what we have now is the idea of an overloaded function. I can put in here int A, int B if I want. And I can even name these the same thing as the A and B variables in there. If I do this, there becomes a bit of a confusion, right? So in order to get this right, I can do this. This A is A, and I can say this B is B, all right? If you just put A and B in here, what variable is in the, in scope here is the closest one logically, right? It'll be these member, or rather the arguments to this foo constructor right here. If I call foo with no arguments at all, it'll run this one up here. If I call foo and I give it an A and a B, rather than setting them to 0 and then expecting somebody to come along later and set A and set B and waste all that time, I can have them set them directly like this. And by saying this A equals A, I'm solving the problem of ambiguity here, right? So this A is the one that's up here, and the one over here is the argument to the function, the parameter, right? So now down here, when I create Y, how do I do that? I put them right in here. 1, 2, 3, 4, 5, 6. This is how you pass the arguments to a constructor when you're creating a Y by value. Compile it, run it. Now again, I see the two constructions. The first one had no arguments, so it used the constructor and set them both to 0. The second time I constructed it, I passed it to these two values, and you can see that it got set up in there. Now, I probably should have said like this, maybe say foo. And I can down here say like foo int like this. Now we can tell which one was called because they have a different message, right? All right. Oops. So we have the idea of constructors. We have the idea of overloaded constructors. The overloading is dependent on, this is called a function signature. What is the signature of this function? This is a function called foo that takes 2 integers. What is the signature of this one? This is a function called foo that is void of parameters. You can actually go up here and explicitly say void here if you want to. It says, I have no arguments. Okay? Run that one and everything is fine. Okay? Now we've solved that problem. What if somebody forgets to initialize it? Well, now they can't forget to initialize it. Now, the idea of a constructor begot the idea of a destructor. So you can say tilde foo like this. Now, when you create a destructor, this is used when the object it needs to be destroyed, thrown away, deleted. You don't delete an object and pass it parameters. There's only going to be one destructor in your class. Okay, let's just say cout tilde foo, just so that we know it got called. There's really not much to do in here. This object doesn't have anything fancy going on. The memory that holds these values will just be thrown away. Okay. We don't need to do anything special. There are times when we do need to do something special. If you have, dynamic memory involved and things like that. We'll talk about that later on. Let's go ahead and print out the this variable in here so we know what has been destructed. Okay? Because this is always valid and always has the address of the current object on behalf which these members are executing. I can even add it down here. I can say func. And put this in here. So now we know which one executed that. And of course, I only know it based on its address. And now it's all messy because I put it everywhere. But you can see what's going on. And see these destructors getting called here? So what happens? Foo is constructed at blah, 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 498. Then func is called, which prints out the A and B values. Then we see the foo constructor for y, which I passed in the 2 arguments, is called here on behalf of the y, which is located at 4A0. Now, I call func on the y instance of foo. I should have put a space in here. This is kind of hard to read. And I then fall off the end of main. When a variable goes out of scope, it will be destructed. And it is a feature of the language that if you construct the x at 498 and the y at 4A0, in this order, they'll be destructed in the opposite order. So I got x constructed, I got y constructed, I destruct y, destruct x, unless I explicitly destruct them myself, which is a whole nother ballgame, right? So they get deleted in the opposite order. You can still see like a stack working in here, okay? So you create an X, you create a Y. When they're done, they go out of scope. When we cross the closed curly within which these things were defined, okay, they'll be destructed in the opposite order. Let's fix our little message here because it was very annoying. What was I? Here it is. I screwed this up. I'll run it once more so we can see better. Because A is also a hexadecimal letter, a number, and the hex value, the addresses looked weird when I ran this, okay? So this one down here, X is at 348, rather A48, and then we see the values here, and then 50 is the address, the ending of the address for the Y, and you see 50 in the A and the B. When I ran it last time, the A's look like they're part of the address. I may have even misspoke. I apologize if that was the case, but I think this would clarify that if you got thrown by that as well. All right, so let's spruce this thing up a little bit. What do we know about these functions? We got the constructors, we got the destructor. This func here prints stuff out, but it in no way modifies the contents of the foo class instance on behalf of which it is run. I can put a const over here. That means to the compiler that when this runs, there will be no side effects of any kind made to this X object. This function does not modify the object. This allows certain optimizations to take place that otherwise the compiler could not assume when it's compiling main over here, because it doesn't technically know what's going on in here. You know, you could argue, oh, it's right here. Why doesn't it look? Well, these can be in different files, okay? They can be compiled at different times. If we run this now, it'll still work. It seems very subtle, but it's true. You want to, again, I mentioned const once before, whenever you can refer to something as const, define it as const, you should. Like right here. These two are also const, right? They don't modify the contents of the object. Define it as a const function, okay? We're all still good. Or making the compiler be able to generate more efficient code, number one. Number two, anyone who uses this class, when they look at the definition of get A and they see const, they too know that if I call this, I'm not going to modify that class. There's no const on here. I know it could, and if it was designed by a competent programmer, probably does have side effects that could cause the instance of foo upon which I call the set B to have some sort of side effects to that thing, all right? Obviously, with a name like set B, it probably does have side effects, and get B probably does not, all right? By convention, these are fairly common conventions that you see other programmers using to name these mutators and accessors. Now let's see something else that we can do in here. As of C++11, additional methods of initializing these variables were provided. If I put curlies after it like this, I think I have to put equals, I can initialize them right here, which is much easier to see when you're writing your code. You don't have to look over all these constructors to figure out what's going on. Now, this may not be the most efficient thing, right? Because what I've done here is I've eliminated the need for that. Now, if I use this constructor down here, what this will mean is first set them to 0, then come down and do this, okay? Now, it is theoretically possible that a compiler might decide to optimize out this initialization up here because the compiler knows about all of this when it does this down here. And a good compiler probably would, all right? So let's go ahead and compile this to show you how that works. All right, we still have the zeros in the case of X, right? The X instance of foo, because we initialize them up here. Now, C++ allows you, rather than putting your code up here, which we call inlined, we can actually provide the code for set A outside of this class definition up here, okay? We can declare a function as a member of the class, and then later on down here, we can provide the body of it down there. You need to, this is very common, all right? Yeah, you might think it's easier to do it, you know, up above, but there's commercial reasons why this is useful to do it like this, all right? Now, how does it know what this is part of? I say foo, :func. I have to have this signature that this function has to match the one up here exactly the same. And because func is otherwise, you know, not affiliated in any way with this class foo, I have to say Func is a member of foo using this notation right here. And we've seen this before with like std : cout and things like that. When I use that notation, that's because cout is a member of the std namespace, we say. Or it could be the member of a class called std. It turns out both of those things are the same grammatical expression here, okay? So what are we going to do now? This should work perfectly fine. And we still see that func runs and prints out what it's supposed to print out. Even though that the body of this function is disembodied from that class instance. I can do that for all of these if I want to. I don't need to. It's just more of the same, and it clutters up this particular example. So this thing here is declared here and defined down here. All right, as we evolve this into all these combinations of things that you could do, look what's happening with this constructor up here. Normally, you don't print stuff out in a constructor. I just did this so that we can see the program run and know that it went in here and ran this code. Normally, these would not be here. I'll comment them out, okay? If you have no reason to create a constructor like this, what you can do here is say equals default. Then you don't have to provide the body of this constructor at all, right? We see it works perfectly. Of course, it doesn't print out anything in the constructor anymore because I removed it. Okay, I commented out these print routines in here, right? So the default constructor simply means do what you would normally do with this curly brace initialization up here. Okay. Now there's another variation of what you see down here that is done. And it looks like this. This kind of goes back a ways. It's like the original way you had to do this sort of thing, okay? If you have an A and a B and a parameter in here, and I have an A and a B up here, I can pass them through on this constructor method to say, use the A here, which is right there, to initialize my A member variable up here. So let's go ahead and call this one AX and BX to make sure we know which one we're talking about here, all right? So this is what it really means. And then, of course, if there's nothing to do, we can just put curlies in here and have an empty body in there. Again, we see it working. Fine, that's the constructor that did this. So obviously the values got in there, all right? Sometimes you see it done the way I drew it here. Other times you can put it all on one line. If there's only one or two like this, I would put it all on one line. But quite often you create an object that's got like a half a dozen things in here, or 24 things in here, would even be worse, and you run out of room. So I tend to, when that happens, I'll line them up all vertically like this. Especially if they all have very long names, you run out of space, okay? Now, I don't think we can put equals default in here. I don't believe we can do this. Let's see if you spell it right. Not. I don't think that's going to work. Let's go ahead and try it. No, it doesn't. I've never tried it before, so this is an education for all of us. If I do this, I put the curlies down there, okay? So in conclusion, what do we got here? A class or a struct is this container-like object, okay? It's an object. In C++, we call that an object, or we call it a class. And that's what we're referring to, okay? It has a name, which is a type. Right? We've introduced a new type of thing called a foo, all right? It has member variables, and it has member functions. This particular member function is a constructor. Here's another constructor. These are overloaded, an overloaded function and or overloaded constructor and or overloaded method. All those are the same kind of thing here. The way they differentiate between them are by the number and types of these arguments. If I had a foo with an int and a float, That would be different than the foo with an int and an int, which is different than a foo with nothing at all, okay? The differentiation between the different functions that have different types of arguments in its signature is what we call overloading. And that's how it's overloaded, by the way. All right, you can overload these down here too. I could have another func if I wanted to. Func member down here that maybe it has a double in here. Oops. And if I do this, by the way, this will still compile and run. Notice I've declared that there shall be a func that takes a double that will be a const. It's a tree that fell in the forest and no one's around to hear it. Nothing bad happens. Why? This is obviously an error. I declared something and I never defined it down here. Well, the reason this is okay, or at least not an error in the eyes of the compiler, is because no one wanted to use it anyway. It's not going to force you to create one just because you declared one up here, unless someone actually uses it down here or somewhere else in your program, okay? So I could do this. And I can even print it all out. I could say whatever, D equals, oops, we're going to have that problem with the space in there again, right? I could put D right here. And if I don't type it in wrong, it will work. All right? And this will still compile. It'll still run. Of course, no one's using it, okay? But now I can actually call it y.func 123, which gets into a whole nother ball game. What's it gonna do now? I called yfunc and I gave it an integer. There are no funcs up here that take integers. There's only a nothing and a double. If I do this, the compiler's going to say, well, I can make an integer into a double and coerce the value of this thing into a double and then call this function. That's what's going to happen here. And it'll call the one that has the D in it. All right? As opposed to the one that does not, which is what gets called up here. And I can do this, 0.456. Now it has a floating point number and or a double in its natural use, okay? So the compiler can do these conversions, these coercions for you, and it can get very confusing at times. Because if I have another func in here that takes an int, just for fun, now it can get real confusing as to what's going on. Let's go ahead and print the I out here like this. Which one will this call? Obviously, that's a double. Which one will this one call? 0. That one should call the int. Now I've left a bug in this program. Let's compile it and see what happens. What did I forget to do? I forgot to declare that the foo class has a func that takes an I. All right, there's no declaration that matches foo func int. Okay, with a const. Oops, my shell history is breaking on me there. You can't just add these things willy-nilly is the point, all right? You have to declare that there will be one if you're going to try to create one later on. You don't even need to name these variables up here, right? If you declare that there will be a func that takes a double or a func that takes an int, that's as far as you need to go up here. The name of this argument is not relevant until you define the body of that function. So this too will compile, and it will run. And we see the double get called when I pass it a double, and I see the int get called when I pass it an int, all right? Now, this thing is getting increasingly subtle, all right? You know, don't do this stuff, you know, gratuitously. And don't force weird type coercions to take place because people can't follow them. They won't understand the code. Yeah, right. If your goal is to confuse everybody and dazzle them with your awesomeness, yeah, sure, knock yourself out. If your goal is to make money with your startup company, don't be a fool because all your employees will screw up your code because they won't understand how it works. And vice versa. Don't hire people that have an ego the size of Texas and tries to write code that is really difficult to understand and uses every possible feature and crazy coercions to make things go. Even worse, the ones that do this by accident. They're the ones that don't understand it and are doing it at the same time. That would even be worse. So keep this to a minimum. Don't wreck your code to eliminate it, but don't do it gratuitously is my point. So these are the basics of what classes are, how they work, how their members work, how to invoke their member functions, whether you're creating them by value or you create one that has a pointer to it, right? And because this is another data type, just like an int or a double or a float, I can create a function up here and does all the usual stuff. I can say, I want a foo reference to a thing called X. I'm going to call it X in this function. Well, let's give it a new name because we're using that too much. Let's call it J so we don't have any confusion about this X down here, right? I declared J as a reference. So when this func up here is called, I can say J.func. And I can say J.func1. And I can say J.func 1.0. All right, this is going to call all three of the above funcs, the one that's void, the one with an int, and the one with a double. And because I said I want a reference to J, whatever one I give it down here, func Y, func X, will be the one that's being invoked down here, right? Again, I mean, this makes sense. I want a reference, so it's just going to work. And again, I have all these funcs, right? I just created a global function called func. Look what's going on here. Got a global function called func that takes a reference to a foo. That func has no relation whatsoever to the func in here that's a member of the foo and all of its overloaded variants, okay? It's probably not the best idea to write a program where you literally call something func, which means nothing at all. You want to name these methods after the operation they're performing so there's some clue based on its name alone what's going on. I did this on purpose to make sure that we all understand how the scope works on these things, all right? Let's say I take this and I want an address of J in here, right? That works too, but because I have a pointer to it, I need to do this. Otherwise, it'll give me an error. Let's go ahead and put an error in there like this just to see what the compiler says. Let's leave this broken down here too. What's going to happen? I'm passing it the X and Y by value, or depending on how this thing is defined, by reference, okay? But we no longer have the reference in here. So what this means now is pass Y by value to this function here. And the compiler says, I don't know how to do that because I can't pass it by value. I need a pointer. And then the compiler is also going to gripe about this because I'm executing a member function on a on a pointer object as opposed to it'll call it a reference probably. Maybe you meant to use an arrow. Okay, so request for member function func in J, which is a pointer to type foo. This is the one where I put the dot in there on purpose. Then later on, it says I want to pass Y down there, which is a type of foo rather than a foo star. Okay, so the compiler does a very nice job at reporting these errors. These are amazing, by the way. The compiler didn't used to have all these little pictures of the arrows. When I learned how to do this, I had to walk uphill to school both ways, blah, 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 blah. Things are a little nicer today. Right, the old joke, you know, back when I was a kid, I had to walk to school uphill both ways. Try and figure out how that's possible, right? Okay, so I fixed the errors in here, right? If I want to pass a pointer to y, I got to put ampersand y, ampersand x. Now it'll work fine. Okay, let's take a little more look at our const friend here. What happens if I make this a pointer to a const foo? What does that mean? Well, luckily, func in all of its forms and glory are const. Okay? If I do this, I'm promising that I will not modify the thing that J points to in the body of this function down here. How do I guarantee that? Well, I guarantee it because the member function of J called func is also declared as const. We call this viral, okay? People that run into these situations where they have a const pointer and they need to call a function that does not take a const pointer, you know, they can't do that anymore. So const becomes viral. Once you pass a const into something like this, it has to stay const in all the contexts within which it's used later on. So this should still compile and run fine. What will not compile and run fine is if I decide to call set A, all right? And this is why we do this const stuff. It gets to the point where you're, you know, many degrees of separation away from what's going on. Oops. And because set A is non-const, it'll say I can't call a non-const function. It discards the qualifiers, all right? I'm passing a const foo as this when I invoke that method, all right? Let's make sure we understand what this means. I have J, which is a pointer to a const foo. And remember what this means. This is the name, the variable name that the object represented by the J pointer over here uses to refer to its own variables, right? So let's see what's going on in the source code really quick here. Set A, when this executes inside here, what this means is that this right arrow A equals I, because the word this is a keyword that refers to the address of the object that this method is executing on behalf of, right? So this is not a const function, and I invoked it using a pointer to a const foo. I can't do that. All right, simple as that. We're back to working again. Okay, I can call anything as long as it doesn't modify the object. I could call get A and get B if I want to. All right, no problem. But because this is const, I'm not allowed to use it as a non-const thing. If I take the const away, I can do this. All right, and that should be fine in this situation. Okay, now I modified it and then I never printed it out again. So let's go ahead and print it out down here. I modified it in both X and Y cases. So why don't we go ahead and run them both before we destruct them. See that that actually got set to 98756 or whatever that was before it went away. And you can see the new values were poked in there by our little global function right here when I did this, okay? What else can we do? I can pass it by value. Now what happens? Let's just do this and compile it. It won't work because I is not a pointer and we're using pointer notation, okay? Here's what's, you know, I'm using the arrow, but I have a non-pointer type. Okay, J is not a pointer. That's what the arrow means. Okay, let's go back and fix that. If it's a value and not a pointer, we put the dot in there. What's this going to do? Well, when this runs, well, these are going to be an error, right? Can't pass a pointer to a function that wants a value. So let's go ahead and see the compiler error for that. I can't convert an address of Y to the, which represents a foo star, to just a regular old foo. It says, no, I won't do that. So you go down here and say, oh, I don't want to pass it by its address. I want to pass it by its value. Now what has to happen, in order to get this function to go, an entire copy of Y needs to be made in order to execute this function. And then an entire copy of X is made to execute this function. All right, there's overhead involved. You generally don't want to pass these things by value unless you have a real good reason to do so, okay? And what's going to happen here? We passed it by value. Therefore, the modifications that were made to the A variable in each of the two X and Y instances is thrown away. Because when it ran the global func subroutine up here, it ran it on a copy of Y and a copy of X. So it printed out the values, right? Because it, grabbed the copies. But when it set A and returned here, it set A on a copy of these and they were thrown away. Now let's go back up here and put this messages back in the constructor here. I argue that you got to be careful about these passing things around by value. Because what's going to happen here is we're going to see, I'm going to get rid of that and put it back in here and put a message in there. These constructors are going to get called to create temporary instances and when it got passed by value. See this destructor right there? This is getting really noisy. Let's get rid of some of the extra gratuitous I/O that's going on here. If we create an X, oops, let's just comment that all out. And we create a Y. Oops. Right, those are the two different constructors, okay? And we pass them by value into this function. It has to reconstruct a new foo in order to make this call. And it has to reconstruct a new foo to make this call. And when the calls are done, it has to destruct them. So what we're going to see is a construction of X and Y. Then we're going to see a construction of a temporary copy of Y and a destruction of the temporary copy of Y. Then we're going to see another construction of a temporary copy of X, a destruction of the temporary copy of X, and then down here we're going to print out the X and the Y and the X values with the call to that method, and then you'll see the X and Y destructed down here. Obviously, there's some overhead involved. Don't pass things by value unless you need to. So what do we got going on here? Here's the destructor. What do we got here? So here's foo and foo. There's your X and Y being created. We call these in the J. I don't think I have my what did I do wrong here? How come I don't see my my constructors getting called for the temporaries? You know what's happening here? The compiler optimized away these constructors. There's a way to force them to go in there. But this is an unfortunate example. The compiler is better than we'd like it to be for this particular example. What it's doing is it's making a copy of the object. We'll talk about this later. This will come back. It's executing what's called a copy constructor. And I did not provide a copy constructor. And therefore, it uses a default copy constructor that does not have the print message in it, okay? But you know it was constructed, or at least you can theorize it might be, because we do see the destructor getting called on that temporary object that's at this address here when the call to when this call is completed. All right. So it creates the X and the Y using the constructors we're familiar with. It makes a copy of Y using a special thing we'll talk about later. And then it invokes this function on that copy. And when it comes back, it destroys it. Then it makes another copy with the copy constructor. And it calls func again. And it will destroy that one when it's done. So you can see the temporaries getting destroyed in here is my point. I forgot about the copy constructor. Anyway, the takeaway of this whole thing is that if you're passing objects around by value, there can be things going on that you may not realize, okay? So don't do this without a real good reason, all right? Quite often in modern C programming, we'll see people doing everything by reference and by const reference when they can, unless they need to pass a copy of something around. And there are reasons to make copies of things, but not gratuitously so. All right. If we do this with a reference like this, now it won't make those copies, and you won't see the extra destructors running in here like we did before, right? Up here, you saw the temporaries getting destructed. Okay. This obviously will run faster. So don't ignorantly be creating things without a good reason to do so. All right, I think that's enough of the basics of classes and how to use them with pointers and references and overloaded methods and constructors and destructors and public and private. If you're having trouble with these concepts, go back to the course website. I've got a link in there to some pages that talk about classes and the basics. You can also Google around on the internet. It's a very well documented subject. You find all kinds of different ways of describing, defining, and using these classes. A lot of introductory tutorials. If this one didn't work for you, just go find one that works better. It may come as an approach that's a little different than what you would get from me, and drive the point home. So thanks for watching. See you next time.